So the code is finally run now. We have the distance computed between the merchants and the customer. It will definitely take some time to run. So in case when you're trying it from your end, don't worry if it's taking a long time. It should take somewhere between 5 to 10 minutes for it to be complete. And now when we look at the distance, you get to see how the distances are computed, right? So for every row you have this distance computed. So this distance is nothing but the distance between the lat long of the customer and the lat long of the merchant. Okay, so now let's look at again the columns, and let's pick the ones that are useful for us for model building. Of course, we had some raw features. With that, we just did some transformations and created our own features like age, distance, so on and so forth. And we basically we just want to drop few columns which we think will not be useful in determining if a particular transaction is fraudulent or not, and we just want to retain the ones that are of some use to us. So in this case, we are just going to retain these columns. We feel that the columns that could be of some use to us are merchant, the category, the amount for which the transaction is done, the gender, state, city, population, job of the customer, age, transaction month, distance, and is fraud. So we are just going to ignore all other columns. For example, this transaction date time is going to be dropped because we just extracted the transaction month from it. Likewise, CC number can be eliminated because those most likely are unique values. Those are bunch of numbers and they won't convey much about the fraud pattern. Likewise, the first name and last name are also more or less with the same idea. We are dropping them. We just cannot tag a particular transaction as fraud or non-fraud just by looking at the name of the person who is performing the transaction. Okay, so we're just going to drop those things and we're just going to stick to only these columns. Okay, so now what we are going to do is we are just going to um, subset this data frame with only these useful columns, and I'm going to create a copy of it. If you're not going to add this dot copy method, you're just going to work with the same data set. It is just going to be a reference that is going to be created. It's not a copy of the data set as it is. So since we don't want to disturb with the original data set and we want to subset and create a new data frame separately, we have this dot copy here. Okay, and when I just now do the head operation, you see that these are the columns that we are interested in, and these are the columns that will be used for determining if a particular transaction is fraudulent or a genuine transaction. So now let's add some more. Let's add some more utility function. We'll just see in some time as to why this utility function is needed. So let's add this function called percentage aggregation or percent agg underscore agg. So that is going to take in a series, a panda series as input, and it is just going to sum the series and divided by the length of the series. Okay, this will be intuitive as to why we need this in some time. So now what we are going to do is we did some kind of feature extraction. All the features are extracted. Now it's time for us to do some descriptive statistics on the data. Okay, or people call it as exploratory data analysis or EDA. Okay, this is very much essential because this gives us a good idea as to where the fraud comes from at a high level, and also we can use our judgment to see if the data makes sense to us or doesn't make sense to us and things like that. So what we are first going to do is we're just going to do a group by operation. Okay, we're just going to group by gender. Okay, so basically we are going to see if there is a significant difference between the fraud behavior between men and women. Okay, that is what we are going to uh, uh, do this by using this gender operation. I mean by this group by operation. So we are just passing in this column called gender, which is already present in our data set. So for every value of this gender, which in this case just two values, male and female in our data set, we are just going to take the sum of fraud, um, the count of transactions that were done, and the percentage aggregation, which is the function that we just wrote here. So I'll just explain the results once we run this cell. So from this result, we see that there are two types of genders in our data set, which is female and male, and for each of these segments, we get to know the sum of fraudulent transactions that were committed by the respective. And also, we get the count of total transactions that were done, and also the percentage aggregation. So this basically tells you what percentage of transactions were fraud from that particular segment. So in this case, this value of 0.526 is basically nothing but it's a ratio of 3735 divided by the sum of the entire transaction, which is this. Okay, so that is what is being computed using this aggregate function. So for every category in this column called gender, we are just taking this column is fraud. We are taking the sum of the values, which is basically going to give you, since the fraud tag is 0 or 1, if I'm just going to take a sum of that column, that is going to tell me the number of frauds in that. Okay, and also the count is going to tell me the number of transactions which were performed, and the percentage aggregation is nothing but the percentage of transactions that were fraud from the pool of total transactions done by that particular segment. Okay, so next we have the same so here from this result we kind of understand that the percentage of frauds amongst men is slightly more than the percentage of frauds amongst female. Okay, next let's try to do the same thing for the month of transaction. Okay, I'm just doing aggregation over month here. So for every month I'm just finding out what is the sum of transactions, uh, sum of fraud, basically what is the number of fraud transactions, number of total transactions, and percentage of frauds in that month. Okay, so that is what is being computed in this step, and here I get the result. So here you see that every month you get the sum of, I mean you get the fraudulent transactions that are happening every month. So for the month of January, it is going to be 849 fraudulent transactions out of 104,000 uh, so on transactions, and that results in a fraud percentage of 0.81. Okay, so like this you get to see this kind of aggregation for every month. So this kind of I mean this kind of descriptive analytics is really needed when you work on any data. So let's say that your data tells you that a lot of frauds happen during the holiday season, which is mostly the year end. Okay, at the beginning of year, the first week of every year. So you tend to see a lot of fraud in those kind of timelines, and if whatever the data also tells you agrees with your understanding, then you can have some confidence in the data. If not, you can just probe more into understanding as to why the difference is happening. Okay, so these are some of the techniques which we use to understand if the data is correct or not. So now what we are going to do is we are just going to plot a bar chart of this data that we have, just to have a visual feel as to how this data looks like. So we are just, so in this cell we are just going to take the required columns, subset the required columns, the month and the fraud percentage in every month, and we are going to do a simple bar plot. So here it tells us the monthly fraud percentage across different months. Okay, so since this is a sample data or a synthetic data, we try to mimic some portion of the reality. So for the month of January, you see the fraud rate is high, which kind of the holiday season continues, and again in February also the fraud rate is higher. But during the dry months of July, August, June, you don't see much of fraud happening. So these are some of the checks that you could do to see if the data is actually valid or not. And now let's try to do one more aggregation. So we have computed this age, right? So we'll do one thing. We'll just try to segment the age into four categories: less than 20, 20 to 30, 30 to 50, sorry, 30 to 58, and people who are elder than 58 will be in segment 4. Okay, so basically this corresponds to youngsters, and this corresponds to people who just entered the job, and this corresponds, segment 3 corresponds to people who are in the job for quite some time, and finally the segment 4 corresponds to people who are rare. Okay. So what I'm going to do is, again I'm just going to create this column called age segment. Okay, and I'm just going to apply this function age segment computer on this column called age. We'll just try to segment this data into 4 groups and see if there is any pattern hidden inside this segment, just to see if youngsters are committing more frauds or retired people are committing more frauds, just to get some sense of this data. Okay, so again I'm just going to call this apply function and pass in this age segment computer, and store the results in this column called age segment. And once again I'm just going to do a simple group by operation, but now I'm going to group by the age segment. So for every age segment I want to know what is the total number of frauds that are committed, what is the total number of transactions that were committed, and the percentage of frauds in that segment. So that is what is being done here, and I'll just get hold of the data here. So from this data, we see that for segment one, the percentage of fraud and the number of fraud and the count of transactions are very less compared to other segment, and this also makes sense, right? Because segment one corresponds to youngsters who are less than 20 years of age, and most likely they will be in college or just doing their like studies. Most likely they won't be doing much of the transactions. In most cases they are dependent on their parents, and so they won't be doing much transaction. That's why the count of transaction um, is also very less here, and so is the percentage of fraud. But if you see people who are in segment 2, which is basically the people between age 20 and 30, you see a lot of fraud occurring. The 61 percentage, I mean 0.61 percentage of the transactions are fraudulent transactions. And likewise, if you see in segment 3, which is actually the working population between 30 to 58, the number of transactions itself is really huge, and this also makes sense, right? Because that is a time when people, lot of people will make a lot of transactions, and that's getting recorded, and this kind of ties to our understanding of the reality. So this data whatever we have here is more or less making sense. So now again let's try to plot a bar chart to understand what this data looks like pictorially. For this we are just going to use this matplotlib library. I'm just going to get the required columns here, I mean required columns, yeah, which is the segment and the fraud percentage, and I'm just going to pass in these two columns and add a title here, and add my labels for my x-axis and y-axis, and you'll be able to see the results here. This is the same data that is shown in a pictorial manner. So this kind of analysis, as I said before, helps you understand or helps you develop faith in the data. So now let's do a simple histogram plot of the distance. We have seen bar charts. We are going to see a histogram. So in histogram is nothing but we're just going to see how this distance is distributed. Um, so there are only very few transactions which are occurring that have more than 140 kilometers between the customer and the merchant, and majority of the transactions are centered around a distance of 80 kilometers between the merchant and the um, uh, customer. Okay, so now again let's try to do some kind of segmentation on the distance. So let's try to have a simple rule. Okay, so the rule is, if the distance is between 0 and the 20th percentile, then I'm going to call it as a near distance. Okay, if the distance is between somewhere 20th percentile to 70th percentile, then I'm going to call it as a moderate distance. If it is more than 70th percentile, I'm going to call it as longer distance. Okay, so that is what I'm going to do. I'm just going to use this method called percentile from this numpy library, and I'm going to pass in this distance column of this df process, train df process, and I'm going to set the cutoff as 20. Okay, and I'm going to repeat this by setting the cutoff as 70. This is going to give me the moderate distance limit. Okay, and when I run this, you get to see the near distance, moderate distance, and long distance limits. Okay, um, so the so any distance between 0 and 49.463 is classified as near distance. Anything between 49 to 94 is classified as mid range, and anything beyond that is classified as long distance. Okay, so again I'm just writing a simple function that incorporates this logic and populates this field near, moderate, and long. Okay, so now it's the same process again. I'm just going to apply this function distance segment computer on this column called distance and get the result. Yeah, so this is the result that we got here after doing this aggregation. But this result tells us that I mean there is not much of difference between the fraud pattern um, between the long, moderate, and near distances, because if you see the percentage of frauds, that's more or less the same. There is not significant difference like what we observed in the previous group by statements. It's more or less the same. So this kind of tells us some information that distance is not a key factor in determining if a person if a transaction is fraudulent or not. Okay, so yeah, so we also have this distance segment here, the age segment we just computed, and we have this we have it in the train df data frame. So now we are going to create the development data or the training data, and we are going to call the x variables as train x, which is nothing but the independent variable, and the y variable, which is the fraud flag, as the dependent variable. We are just going to separate it out for the modeling purpose. Okay, so now within the data that we have, certain columns are categorical in nature and certain columns are numeric in nature. So categorical columns have to be processed differently when compared to numerical columns. The categorical columns in our case are merchant, category, gender, state, and job. So these are basically the categorical columns, and we have to do some kind of pre-processing to pass it as an input to our model. Okay, so we see here you have this train x numeric that is going to be the numerical features of the data. I'm going to take this train x that was created and drop these features, which are nothing but my categorical features, and in the next line I'm just going to subset these features. I'm going to call it as the categorical features. Okay, so this is how my categorical features looks like. So when we look at categorical feature processing, that's topic. I mean that's a whole topic to discuss. But here we are just going to stick to what is called as ordinal encoder. Okay, there are many ways to handle categorical variables like one-not encoding, weight of evidence, so on and so forth. But here, for the sake of simplicity, we are going to do what is called as ordinal encoder. So what this ordinal encoder does is, it is just going to take the categories one by one, and it's just going to replace it with a number. So let's say that we have this categorical column called state, and let's for example let's say that it has 5 unique levels, which are NC, WA, ID, MT, and VA. Okay, and what this ordinal encoder is going to do is, it is just going to replace every category with a label. So NC is going to be labeled as 1, WA is going to be labeled as 2, ID is going to be labeled as 3, MT is going to be labeled as 4, and VA is going to be labeled as 5. So the now, so basically the maximum label that you will be seeing is nothing but the number of unique values that is there in the like data set. Of course, in certain packages the numbering will be from 0, so it will be one less than the unique number of levels that a particular feature has. Okay, so that's what we are going to do here. We are just going to import ordinal encoder from scikit-learn's pre-processing package, and we are just going to uh, use this statement for doing this encoding. So here we have this parameter called unknown value minus 1. So what this basically does is, so let's say that during training time you have just seen 5 unique values for the state, okay, and for each of these values you have an encoding like readily available, okay. But during inference, during testing, let's say a new category comes in which which is not there in your training. So what should be the label for that, or what should be the encoding for that? There needs to be some kind of standard, right? How to handle these unknown categories that I'm going to see or will be seeing in the testing environment. That we have this that's what we call it as minus 1 here. So anything which is unknown, which is not seen in the training set, will be tagged as minus 1. Okay, so yeah, I'm just quickly running the code here. So I'm just going to take the training data set, and I'm just going to fit this encoder on it. And once the encoder is fitted, I need to do this transformation. So this fitting will just create the mapping and store it as a metadata, and then when I apply this transform method, it will try to do the actual encoding. So here I'm just going to um, call the new data frame as train x categorical encoded, and yeah, this looks something like this. So for all the 4 category, all the 5 columns now have a numerical value in it. So initially they were uh, categories, the raw categories as it is, but now we have just change it to numerical representation, okay. So now but when we look at numerical columns, again we need to do some kind of pre-processing like missing value treatment. You're going to use neural network or any algorithm that is based on gradient descent, then you need to make sure that your numerical columns are also normalized. But since we are just going to go with decision trees for now, we don't have to care much about the normalization aspect. Since this is a synthetically generated data, we also ensure that there is no missing data available, missing data. So we have the final train data that is ready. So now we are going to do the same process to our testing data, okay. But there's a slight change to this, okay. When we do the testing data, we are not going to do the fit of the ordinal encoder. Ordinal encoder is already fitted using the train data. We are just going to do the transformation, okay. This is to prevent something called as data leak, okay. All the categories that you are seeing should be only from the train data. You should not use test data for fitting your ordinal encoder. That is what is taken care in this line, where we just try to use the transform method and not the fit method, okay. So rest all operations are just the same that we did for training data. We are just getting the age, the transaction month, the distance, and then we are just separating the dependent and independent variables, and then we are just getting the categorical and numerical separately, and then we are just doing the encoding and doing some kind of concatenation. Now again, this snippet is going to take some time for us to run because of the bottleneck code, which is this line, which is basically computing the distance. So I'll see you on the other side once the code is run. Yeah, the code is ready now. So now let's look at the shape of our train data and test data, okay. um, so yeah, you have closed about 1.29 million um, records in your train, and you have closed about 55,000 in your test, and we have closed about 10 features, okay. So now what we are going to do is we are just going to import all the packages that are required for model building. As I mentioned earlier, we are just going to work with decision tree classifier. So any tree based model, be it like random forest or boosting techniques on trees, are proved to be working better, okay. So that could be a very good starting point if you are going to set something like a baseline, okay. Yeah, I'm also importing few additional functions like confusion matrix, confusion matrix display and classification report that is going to help me in computing those metrics that we just saw in the theory session. Yeah. So now I'm just going to build my model now. So I have the data ready. So I took the raw data, did some kind of pre-processing and extracted the features, and then I did some EDA on it to understand the data better. And once I got the data, I basically try to clean the data and do some kind of um, uh, a categorical variable treatment. And once it is done, I'm just done with the data preparation. And now for model building, all I have to do is just execute this one single line here. Okay, I'm just creating a decision tree classifier object here. I'm just going to create a decision tree with the maximum depth of only 10. Okay, um, since this is the purpose of just illustration. So as you can see, the model building is just one line. It's a very simple task, but majority of the time is spent in understanding the data, cleaning the data, make sure the data is correct. Yeah, let it run for some time. So the training is done. So you can see that we have successfully trained fraud detection model. So now let's try to decode it a little bit and understand the results better. Okay, so what I'm going to do is I'm just going to predict on my trained data, and I'm just going to get the confusion matrix. So confusion matrix is what we saw earlier. We're just going to get the confusion matrix, and we're just going to plot the confusion matrix in a aesthetically appealing manner. So that's what I'm going to do here. So here you got the confusion matrix. So here if you see, this is on the train data. Okay, so this column over here is basically nothing but your uh, true negatives. Okay, your prediction is also genuine and your true label is also 0, which means that it is a genuine transaction, and the model was also correct in saying it is a genuine transaction. So this cell contributes to your true negatives, and the diagonally opposite one will be your uh, true positives. The model was correct in saying that the transaction was fraud, and the actual label was also fraud. And this cell corresponds to those transactions where your model was saying that it was a fraudulent transaction, but actually it would turn out to be a genuine transaction. So these were nothing but a false positive. The cell corresponds to 908, corresponds to a false positives, and the one that is diagonally opposite to it is nothing but a false negatives. The model is saying that they are uh, genuine transactions, but actually they are fraud transactions. So this is how a confusion matrix looks like when you do it on a real data set. Okay, so now let's try to compute the precision recall and F1 score metrics using this function called classification report. So you could either, so now you know which cell corresponds to which element, whether it's true positive or false positive. You could compute these precision recall F1 score numbers manually, or you could just use this package function called classification report, pass in your predictions and the true labels, and you'll get the results automatically. So here if you see, you get class wise precision recall. So we're just going to consider all rows which are labeled as 1 as fraud, and the ones that are labeled as 0 as non-fraud. So my this row corresponds to computations that are carried out by considering 1 as positive and 0 as negative. Okay, you see the recall is 0.76. So we could very well confirm it here. The total number of positives that were predicted correctly are nothing but 5670, but the total positives that are out there are nothing but 5670 plus uh, 1836. Okay, so this is nothing but the true positives divided by true positives plus my false negatives. So this is nothing but my false negatives. So we find out this ratio, that is nothing but 0.755, which is approximately 0.76. Okay, like this we can also compute precision, which is nothing but the ratio of true positives divided by true positives plus my false positive. So instead of 1836, I have to replace it with 908, and I will be getting my uh, precision number, which is 0.861. You are seeing the same here. and F1 score, as I said before, it is nothing but the harmonic mean of precision and recall, which you can just refer to the formula that we just discussed and computed. And support is nothing but the number of data points that are from that particular class. So if you look at the class balance, so let's look at the class balance that we are currently working with. So if you look at the class balance, so out of 1.2 odd million records, close to about only 7508 records are only positives, and the remaining are all negatives. So if you look at the class balance ratio, it's going to be very skewed. It is 7506 divided by 7506 plus 1289169. Okay, yeah. I'll just add 100 here just to get the answer in percentage. So if you look at this data, the fraud percentage in the data is 0.57. Okay, so if I'm going to predict all my transactions as good transactions, genuine transactions, then my accuracy will be 99.43. Because for the form 0.57 percentage, we would have mislabeled it as non-fraud, but they're actually fraud. So having a very high accuracy doesn't mean that the model is doing good. Okay, and that's what the support means. And the same numbers are computed here, but by flipping the definition of what positive is. Okay, here 0 is considered as positive and 1 is considered as negative. Okay, and here you see numbers as 1, all because this cell over here is having very high number. It's uh, close to about 1.3 into 10 power 6. So that completely dominates, and then our values are very close to 1, and that's why you see full ones here. And here nothing here, macro average is nothing but the average between these two, the simple average. So for here, if you see the macro average of F1 score, it is nothing but 1 plus 0.81 divided by 2, and weighted average is nothing but the weighted average of F1 score, which is nothing but 1 multiplied by the support plus 0.81 multiplied by the support divided by the total data points. Okay, that is what you will be getting in the macro average and weighted average. But you can just focus on the recall for now, because that is what is more important for us now. We are just going to make an assumption that the organization is more interested in capturing all frauds that are out there. So from this model is doing a job of uh, capturing 76% of the frauds in the development data set. Okay, now let's try to do the same thing for the testing data set. It's just the same code, except that I'm feeding in my test data. Instead of train, I'm just feeding in my test data. Okay, so here when we try to find out the numbers recall, so you can see that the model is having a recall of 0.65 in the test data set. Of course, this difference is kind of huge. You have close to about 10% difference between your recall of your test data and train data. You could do some kind of hyperparameter tuning to reduce this effects. So this is mainly because of the overfitting that is happening. Okay, you could always come up with some kind of hyperparameter tuning experiments and find the right set of hyperparameters to address this problem. Yeah, so as of now, if you see, we haven't done anything special with respect to modeling, right? Even for regular credit underwriting models, we will be doing the same methodology. We haven't accounted for the class imbalance that is there. Of course, we have accounted for it when we find out the evaluation metric or which metric to focus on, but we haven't taken any measures in the modeling approach during the modeling itself. Okay, so that is where we do something called as class weights. Okay, so without getting into the mathematical details of what class weights is, so when you try to build model, then this class weights idea is applicable to almost every model that is out there, be it a neural network, be it a logistic regression, and tree based models. So here I'm just going to give a class weight of 1 is to 10. So I'm just going to create a dictionary where the keys of my dictionary in this case are 0 and 1, which is nothing but the labels that I have, zeros and ones, and the class weight for 0 is 1, the class weight for my 1 is 10. So what this basically does is, I'm sure you must be aware of the loss function with which the models are trained. So here um, the importance basically given to the fraud class is 10 times the importance given to a non-fraud class when the model is being developed. So if a model is making a mistake in classifying a fraud data point, the penalty which or the loss which the model is going to get is 10 times um, as opposed to what the model is going to be penalized for classifying a genuine data point as a fraud data point. So that is what I mean by class imbalance. So this kind of class, this is what I mean by class weight. So this kind of class weight will make sure the model to focus more on the fraudulent cases and try not to make any mistake in classifying the fraud cases. So that is what is happening here. So all we have to do is we just have to pass in a class weight as a parameter, which is a dictionary in this case, and this 1 is to 10 is something that you can just play around. Just for the sake of demonstration, I've just put it as 1 is to 10. Okay, so now let's run this. So ideally what has to happen is when we do this kind of class weighted decision tree, your recall should increase, because now the model is being penalized 10 times for making a mistake in the fraud classes compared to the non-fraud classes. So the model is more focused, or it won't afford to make a mistake in the predicting the frauds. So that way it will be it will improve the recall, and that's what we are going to see as well. So now we are going to get the train metrics. Yeah, the confusion matrix, and then we have the recall of the train data. So earlier, if you see, if I just scroll up, the recall from my train data was 76. Okay, this was the recall that I got in my train data. But now after adding the class weights, my recall went up to 87 percentage in my train data, and that is what I wanted as well. I want my recall to increase. So now let's see how this fares in my test data as well, and see if the same increase is reflected there as well. Yeah, it has increased. If you see here, the recall in my testing data improved from 65 percentage to 82 percentage, which is a much significant number. So now the model is more confident, or I should not say confident, the model is more aware in predicting once. The model doesn't want to make any mistake in predicting once. It is doing a good job in predicting once. So yeah, so that's about the model building when it comes to supervised learning for fraud detection. So the key aspects to keep in mind is, whenever you're dealing with fraud detection problem, most likely you will be in this problem of class imbalance. So there are a couple of ways to handle class imbalance. So one approach that we saw here is by changing the class weights. Okay, there is also another approach whereby you sample the data, where you just do some kind of oversampling of your minority class and undersampling of your majority class, just to improve the class balance, and then apply the class weights on top of it. So from 99.5 class balance, maybe after sampling you will boost it up to 90-10. Okay, 90% being good class, 10% being bad class, and after that you just try to apply class weights on it. But all these are experiments. No one knows what is the correct approach before conducting the experiments. Only when we conduct more and more experiments with the data that we have, we will be sure as to what works and what doesn't work. Okay, so yeah, that's about this section. I'll see you on the other side for the anomaly detection part, where we are just going to assume that we don't have any kind of label to guide the training, and we'll see the benefits in seeing the same problem from an anomaly detection perspective, or basically from the unsupervised perspective. Yeah. That's it. I'll see you on the other side.